Okay, our next step is to discuss Bohr's model of the atom. So let's get straight to it. Let's call it Bohr's atom. Bohr is, of course, Niels Bohr, a Nobel Prize winning monumental physicist that was extremely important in the evolution of quantum mechanics. Um, and so he proposed a model of the atom that, in retrospect, we know to be relatively crude. And the ideas are not entirely correct. In fact, they have to be changed in a pretty fundamental way using quantum mechanics. But the agreement of his model for the hydrogen atom specifically with experiment is remarkable. It is just a kind of an incredible achievement of human intellect. And so let's talk about Bohr's model of the atom. Bohr made two important assumptions in thinking about atoms. His model of the atom was invented after it was already known that the classical electromagnetic theory had a lot of trouble with light, and that the concept of a photon would have to be invoked, the idea of a quantum of light. And so building on these ideas, but also building on them in a pretty radical, pretty transformational way, Bohr made a couple of critical assumptions. Number one, he said that, first of all, that atoms should exist, which sounds ridiculous, but what he was trying to say is that an atom should be a stable thing. What does it mean for an atom to be a stable thing? If we think about, in a very crude sense, that the atom, the simplest atom, the hydrogen atom, is a single proton with an electron moving somewhere around this proton. If the electron is moving in a non-straight or circular or manner, or any manner in which it changes its direction, the electron will be accelerating. Acceleration is not just the increase or decrease in your speed in a given direction, but the orientation of the velocity vector changing is also acceleration. So if the electron is moving in some complicated fashion, or even if it's moving along a circle, it will be accelerating. And classical electromagnetic theory shows that a charged particle that is accelerating should be continually emitting radiation. And if the electron were to be continually emitting radiation, i.e. light, electromagnetic energy, it would be continually losing energy by conservation of energy. And if it was continually losing energy, eventually it would lose all of it, and by attraction to the proton, since they are oppositely charged, it should fall into the nucleus. So the atom should not exist. It should be unstable. Bohr said, I'm going to assume that it's stable, given that we know that things are made of matter and you can show experimentally that atoms exist. The second critical assumption that Bohr makes is that the action that we just defined, the action quantity for an electron moving in an orbit around the proton, is quantized. Cannot be any possible value, like we saw last time where we said the action was 2 pi mvr, which meant the action could be any value depending on what the speed is and what the radius of the circle is, what the mass is, and that the action would change continuously as the speed of the particle changed. Bohr said that's no longer the case. I'm going to assume that the action can only assume integer multiples of some specific number. So not any possible action, but specific increments of action. Those were two really critical, extremely creative assumptions. And so the assumption, the model that Bohr first discussed or described was that of a proton with an electron moving in a circular orbit around it. So this is the electron moving around the circle. The radius of this orbit we're going to call r. So there is a proton sitting at the center, and there's an electron moving in a circular orbit around it. What does it mean for the atom to be stable? If the electron is moving in the vicinity of the proton, it's going to interact with it electrostatically. There's going to be an electrostatic attraction between opposite charges, which tends to pull electrons and protons together and make them want to be on top of each other. The fact that the electron is moving along a stable orbit, by virtue of moving in an orbit, of a circular orbit, it will have some centrifugal force associated with it that keeps it moving in this kind of a circular fashion. And the assumption that the atom is stable is a statement that the centrifugal force ought to be exactly balanced by the electrostatic attraction between the electron and the proton. That's Bohr's assumption number one. What are these forces? Let's write this down. The centrifugal force is the mass of the particle times the acceleration, the radial acceleration, the circular acceleration as the particle moves around the circle. The centrifugal force F, how should we call this? Maybe sen. Can't even tell that I wrote sen. Sen is equal to m v squared over r. The electrostatic force between any two charged particles, or let's call it the electric force. The electric force, let's call it F elec, is equal to minus 1 over 4 pi epsilon naught charge on particle 1, charge on particle 2 divided by the distance squared between the two particles. 4 pi epsilon naught are all constants. Epsilon naught is called the permittivity of free space. Doesn't matter what it's called. For us, it's a particular constant. Charge on the first particle, the magnitude of the electric charge on the first particle, magnitude of the electric charge on the second particle, the distance between them squared. In this case, r is the distance between them. If you haven't seen this force before, which might be completely reasonable, you should note that there is a very obvious analogy to a force that you almost certainly saw in your physics classes, and that is the gravitational force. So compare with F gravity, which looks like the gravitational constant g, mass of particle 1 or mass of particle 2 divided by the square of the distance. And so the correspondence is that in gravity, it is the two masses that interact. In electric phenomena or electric forces, it is the two charges that interact. The strength of the force between the two charges is proportional to 1 over the distance between them squared. So we speak of the inverse square law. The force of gravity is proportional to the magnitude of the mass 1, magnitude of mass 2, and the square of the distance between them in the denominator. The constant of proportionality that connects this business to the magnitude of the force here is we call the gravitational constant, g. Here this constant is 1 over 4 pi epsilon naught. And so the force, functional form of the force law is nearly identical. So the comment or the statement that this electron moves in a stable circular orbit is a statement of the equality of the two forces. So F sen equals F elec, or mv squared r equals minus 1 over 4 pi epsilon naught q1 q2 r squared. Before we go further, let's say who these charges are. Charge on the electron is equal to minus E. Charge of the nucleus, let us be general. Instead of saying that we have a single proton, let's account for the possibility that the nucleus may have multiple protons. The charge on the nucleus is plus ZE, where Z is the atomic number. And so for a proton, of course, it's just for a single proton, for the hydrogen atom, it's just plus E, exactly equal and opposite to the charge in the electron. And so if we put this together, we get mv squared over r equals plus now 1 over 4 pi. Actually, let's just group it together. ZE squared over 4 pi epsilon naught r squared, where the minus sign has gone away because one of the charges is negatively charged. So this is the stability condition of a circular orbit that Bohr assumed, even though this nominally contradicts the idea that charged particles should radiate energy and ultimately fall into the nucleus. And in making that statement that no, the atom in fact is stable, he was led to this conclusion. That's assumption number one. That's what resulted from that. It connects these variables in this specific way. Assumption number two said that the action of an electron as it moves around a circular orbit is quantized. Sure. Okay, make sure I don't write down something wrong accidentally. Action A is quantized, i.e. it can assume only integer multiples of a specific number. Can't be anything at all or anything possible. Can be some values, but some very specific values separated by integers. And so the action is 2 pi mvr, and it's equal to, if it's quantized, to the quantum number n, which is an integer, 1, 2, 3, so on, times a constant called h. It is found that h is Planck's constant, the same constant as what is the proportionality constant between the frequency of a photon and the energy of a photon. So this is Planck's constant, which tells us, interestingly, that the physical meaning behind Planck's constant is that it is a quantum of action. It is the indivisible unit of action. And that the action of the electron as it goes around the ring is a quantized quantity. It can either be h, or 2h, or 3h, or 4h, and its basic unit is h. And so h, Planck's constant, should be thought of as the fundamental quantum mechanical action, unit of action. It's kind of an interesting thing. You know, when we first defined action, it seemed like kind of come out of nowhere. But now we see its physical significance. And so Bohr was led to this conclusion, and of course for us this seems to come out of nowhere, like why did you quantize the action and not something else? What we're omitting is that the action was a very prominent variable that was already kind of, in many respects, at the forefront of classical mechanics of that day. And there were other examples where, to connect with experimental findings, to be consistent with experiment, one needed to propose to quantize the action. And so Bohr extended this idea to the atom. What are the consequences of all of this? The first consequence is that the orbit of the electron can assume only integer values. If we solve for r, in fact, let's label it r sub n to indicate that the value of r depends on the integer n. And so if we solve for r, we find n h over 2 pi mv, where v is the speed of the electron. And so there's going to be n possible orbits with the distance from the proton growing larger and larger and larger in integer values. This gives rise to the first idea, what we eventually come to know it as an orbital, right? With different quantum numbers. And so the distance between the electron and the proton depends on this quantum number n and all the other things in here, including Planck's constant. That comes from the second assumption that Bohr made. The next question that we want to ask is, what have we learned about the energy of the atom? The energy of the atom is obviously an extremely important quantity for us, but from the perspective of chemistry and light, we need to know, we will ultimately discuss that the atom absorbs light and in so doing has an electron jump in Bohr's model from one orbit to the next, from one n to the other, from one Rn to another Rn. And so in absorbing light, which are quanta, which are photons, packets of energy, the atom or the electron in the atom absorbs that whole unit of energy from the light. But because the electron can only have certain energies, as we'll find, the energy is quantized, we need to know what possible frequencies of light, what possible energies of photons the atom could absorb. And in so doing, we can discover the absorption spectrum of the atom. And the absorption spectrum is one of the most important characteristics of a molecule as it interacts with light. And of course, if you want to think really far ahead, knowing how the absorption spectrum of molecules inside chloroplasts in a plant, what the absorption spectrum looks like, can tell you what colors from the sun are most effective at stimulating photosynthesis. And so this has very far-reaching consequences. So let's come back to this. Let's leave this over here. Let's go back to the first condition that said that the forces, the centrifugal force must be equal to the electric force between the electron and the proton for the electron to be stable and to continue to be moving in an orbit. First, let's write down the total energy of the electron. Total energy of the electron. Actually, you know what? Before we go to the total energy, let me work with this a little bit more. One thing that's undesirable here is that for us to know what the value of the orbit is, we need to know what the speed of the electron is. We certainly know the mass of the electron, and we know Planck's constant. It's a constant. And once we know what the quantum number is, we would in principle be able to figure out the orbit if we knew what the speed is. But what is the speed? Who tells us the speed? The value of the speed comes from or one can determine the value of the speed as it relates to the orbit by another equation from the first assumption that we made, the equality of the two forces. So remember what we said. We said that mv squared over r, the centrifugal force, was equal to ze squared over 4 pi epsilon naught r squared. So we're just going to solve for v. Let's solve for v. V equals ze squared. R will go in the numerator. Cancel one power of r in the denominator. And so in the denominator we have 4 pi epsilon mass from there. 1 power of r. Whole thing to the 1/2 power. We're then going to just stupidly substitute this v into the equation for the orbit. Let's see what we get. So r equals, let me make sure I get this right, nh over 2 pi m. Now this whole business, ze squared over 4 pi epsilon naught mr to the 1/2 power. let's work with. So let me now rearrange this a little bit, make this a little bit more compact. And let's write this over here. So we have NH NH, this guy goes in the numerator, times 4 pi epsilon to epsilon mass to the 1/2 power. And I'm going to separate out r to the 1/2 power. Divided by 2 pi m. Now, let me make sure I have everything right. Yeah, okay. Let us, so one thing to notice is that we have a r on the left side and r to the 1/2 power on the right side. Let's pool all the r's together. And so we're going to divide both sides by r to the 1/2. And what that will give rise to, is, I'm going to just keep writing here. R to the 1/2, because this r to the 1 divided by r to the 1/2 takes us to r to the 1/2, equals NH 4 pi epsilon naught m to the 1/2 power divided by, oops, forgot my z e squared to the 1/2. Divided by 2 pi m z squared to the 1/2. And now let's square both sides to get this to be r. Remember, we can keep writing this as Rn if we want, just to really remind ourselves that this is the quantized orbit. So Rn is going to be equal to n squared h squared 4 pi epsilon naught m divided by 2 pi, I'm sorry, not 2 pi, 4 pi squared m squared times ze to the 1/2 power. So this mass is going to cancel this power of m. This 4 is going to cancel that 4. This square of pi is going to cancel that pi. And so what we're left with, make sure I got it right, n squared h squared epsilon naught over pi z e squared m. These should be squared, not 1/2. Apologize. So this is Rn. This is the value of the orbit in the Bohr atom model that allows you to calculate the Bohr orbit if you know what Planck's constant is, epsilon naught, m, e, z, and n. And you do know all of them. So take the hydrogen atom, which will have z equals 1, and let's say what is the distance of the electron from the proton when n equals 1, the lowest possible orbit. The lowest possible orbit will have the smallest possible r. So it's really what we now think of as the ground state of the hydrogen atom. In the ground state of the hydrogen atom, when it's closest to the nucleus, closest to the proton in this hydrogen atom, once you plug in the values of h, epsilon naught, m, e squared, z, and so on, Bohr has made a prediction. He said that you should expect to find so-and-so. And what you should expect to find is a quantity that's something like half a picometer. That is in fact what is found experimentally. The agreement is in fact excellent, remarkable agreement. And so this is the distance that the electron is away from the proton depending on the quantum number n. And as n increases, so does the distance from the nucleus. Now let's do what I started doing earlier, but did so prematurely. By the way, using the same ideas, you can solve for instead of eliminating the speed to solve for the orbit, you could eliminate the orbit to solve for the speed of the electron as it goes farther from the nucleus as the quantum number increases. So let's now think about the energy. Total energy of the electron. Total energy of the electron. We're going to label it as E. And the total energy is going to be the sum of the kinetic and the potential energies of the electron. The kinetic energy we're going to label as K. The potential energy we're going to label as U. So this is kinetic energy. Kinetic energy. This is potential energy. Where the potential energy is an energy due to some kind of interaction. And so this is going to be due to the electric or electrostatic interaction between the electron and the proton. The kinetic energy is just simply going to be the energy of motion, right? So this is going to be equal to 1/2 mv squared, where v is the v of the electron, or the speed of the electron. The potential energy is the electrostatic potential energy, as we said. What is the electrostatic potential energy? Well, it turns out that if you know the force, which we do, the electric force that we wrote down before, you can discover the electrostatic potential energy. Here's what that will look like. Generally speaking, the force is equal to minus the derivative of the potential energy with distance. So the force on, let's say, two charges, the force that each of the charges experiences at a given distance between the charges depends on the derivative of the potential energy with respect to that distance at that specific distance that you're interested in. And so if we, given that we know the force, which is minus 1 over 4 pi, actually, let's incorporate our charges, plus 1 over 4 pi epsilon naught z e squared over r squared. To get the potential energy, you would simply integrate this function. You would find the antiderivative. And what you find is that the answer is minus ze squared over 4 pi epsilon naught r, 1 power of r, not 2. And now minus as opposed to plus. But remember, we know something about this. We know something about this from the condition that the atom has to be stable. Remember what exactly we know about this? Well, we said that the centrifugal force has to be balanced by the electric force. We said that mv squared over r has to be equal to ze squared over 4 pi epsilon naught r squared. Squared because it's the force. Here it's a single power because it's the energy. Remember, they're related through the derivative. And so we can solve for mv squared to plug it into that formula. And we find mv squared multiplied by r on both sides. Multiplying by r will undo one of the powers. ze squared 4 pi epsilon naught r. Plug it in. Find. Make sure I get this right. 1/2 ze squared 4 pi epsilon naught r minus ze squared over 4 pi 4 pi epsilon naught r, which is equal to ze squared 4 pi epsilon naught r times 1/2 minus 1, which is equal to minus Z squared over 4 pi epsilon naught r. So the total energy of the electron as it goes around its stable orbit around the nucleus depends only on the distance between the electron and the proton, because the condition of the stability of the atom forces the kinetic energy to itself be related to the electrostatic force or the electric force, and this gives rise to this kind of an expression. Total energy of the electron, the sum of the kinetic and the potential energy. But wait, there's more. Remember that we know something about r, the orbit, as it depends on the quantum number n. Let's plug that in and see where that leads to for the expression of the energy, as the energy now depends on the quantum number n, i.e. the energy is quantized. A groundbreaking result from Bohr's model, with immediate experimental implications that can immediately be tested. And they were in fantastic agreement for simple atoms like the hydrogen atom. Remember that Rn, let me write this down again. Rn, the orbit of the electron, or the distance between the electron and the proton in a given orbit specified by the quantum number n, is n squared h squared epsilon naught over pi z e squared m, so that when you incorporate all of that, the energy at a given quantum number, i.e. quantized energy, quantized total energy, is equal to minus z squared e to the fourth power. Why to the fourth power? Well, the energy already had an e squared in the numerator. Now you're dividing by Rn, which forces that to go in the numerator as well, and so you get a power of e to the fourth times the mass. This comes from the Rn, and dividing by Rn again brings it to the numerator, divided by 8 epsilon naught squared n squared h squared. This is where the quantum number is. Or can also be written as minus some kind of a constant, call it c, z squared over n squared is often a convenient way to write this. This constant is equal to, I'm sure, 13.6 electron volts. An electron volt is a unit of energy. How do you know this has to have units of energy? Because z is unitless and n is unitless. Right? Z is the atomic number, which doesn't have units. N is the quantum number, which also doesn't have units, so the units have to come from C. This is related to something called the Rydberg constant. So this is a unit of energy. You should look it up, what the unit of energy electron volt is. Extremely useful for a chemist studying interactions of molecules and light. For example, the energy of green light is approximately 2 electron volts. The energy of blue light is approximately 3 electron volts. And so on. So it's a useful number that isn't too high, that is right in the realm of optical phenomena. If you were to plot the energy level for given quantum number n as little ladders, stairs on a ladder, you will start with n equals 1. N equals 2. N equals 3. N equals 4. N equals 5. And so on. They become closer and closer together. And so these separations in energy between adjacent quantum numbers n decrease. I wonder what implications this has for absorption of light. Something we'll think about. And so that's the Bohr model of the atom. What you find is that if you apply the full machinery of quantum mechanics, which is the superior theory that has been found to be correct, one still gets the exact same answer. And so Bohr was very visionary in this model, even though the assumptions that he made in some respects are difficult to justify. But in quantum mechanics, the solution comes out naturally. But nevertheless, he got there. Okay, that's it for now.